Welcome to our Chapter 9 study guide covering significance testing. So, back in Chapter 9, when we first learned about significance testing, there was just so much going on that you had to learn about. There was setting up hypotheses, there was checking conditions, there was learning what a p-value is in the first place and what to do when you have it, how to make a conclusion with one of these problems, type 1 error, type 2 error. There was a lot of info that we covered in this chapter. At the time, there was plenty to test you on just with that stuff. But pretty much all those things that I just mentioned, we did again in Chapter 10 and Chapter 11, and even a little bit in Chapter 12. So you guys are pretty used to by now how to set up hypotheses and do stuff like that. So what I'm focusing on in this chapter is going beyond just, what's HO and HA? And I'm trying to get at some of the harder concepts of the unit. So we'll talk about power in this quite a bit and some of the other finer details that maybe you're not quite as sure on. So when we're going through this study guide, if you do have problems that are like a little shaky where you're not getting as many right as you usually do when we do these, I do think this chapter, this study guide is a little bit trickier than some of the ones I've given you in the past. So no worries there. So let's go ahead and jump in. Our first problem right here is testing a mean. We got mu equals 60 versus mu not equal to 60. We get a sample mean of 58 and a p-value of 0.04. So we're not finding the p-value, they're just telling you what it equals. If your p-value is low, it means the results we got from our sample are unlikely to occur by chance. So this 58 that we actually got in the problem when we collected our sample data only has a 4% chance of happening by chance, assuming that the answer is actually 60. So what that would tell us is 4 is kind of low, pretty low percentage right there. That probably tells us the 58 wasn't just due to chance, and it probably is more due to the fact that the mean isn't 60 like we assumed it was going to be. So if your p-value is low, it gives you convincing evidence for HA. HA, you got to find if the evidence is strong enough for it, and low p-value means it is. So that means that there is sufficient evidence that mu is not 60 because our p-value was under our significance level. They used a 0.05 level. We're lower than that, so it's convincing in favor of HA. So first problem answer is E. Moving on to our second question here. We're doing another significance test on a mean. So mu equals 2 versus mu not equal to 2. And then we have a sample size, blah, 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 test statistic. When they give you a test statistic in a problem, whether it be a normal problem or a T problem, the test statistic operates under the standard normal or standard T distribution. So what do I mean by that? Centered at 0. The 2 from the problem isn't really going to be that important to us. Wow, I can't draw a curve right now. It's not going to, the 2 doesn't really matter that much. If we use a test statistic, our center is at 0. Now with the T of 2.051, that's like way over here on this side. But this problem is actually going to be a not equal to problem. Since HA is not equals, this is a two-sided test. So I not only care about this area right there on the right, I would also reflect that over and do negative 2.051. And I would want the left side of that too. So what I would need to do on this problem right here, they want to know what the p-value is. The p-value is your shaded area in this problem. Everything beyond 2.051. And everything from negative 2.051 to the left. So these two parts right here circled. So what I'm going to do with this is a tcdf command on my calculator. And I'm going to calculate just one of those areas. So I'm going to get this guy right here. And once I do that, I will just double it to get my second tail as well. So if you do a tcdf, you need to make sure the degrees of freedom for this problem. Remember that degrees of freedom are always your sample size minus 1 for a one variable problem. So I have 27 degrees of freedom. My lower would be 2.05, blah, blah, blah. You're going to find out that this is just over 0.025. If you double that, you get just over 0.05. And even if it was exactly 0.05, the less than or equal to sign is right here. So our p-value is going to be somewhere between 0.05 and 0.10 after you do your tcdf. Answer on this one, also E. Third multiple choice question is talking a little bit about conditions. We have yet another mean problem here for this third one. And in this problem, we took a sample of size 5. So we have 5 soybean plants, I think. Yeah, 5 soybean plants, and we're measuring their protein compared to beef. And those are our data points. They want to know which of these conditions do we have to satisfy in order for us to actually be able to carry out a test like we learned about in this class. So let's address sample size first. The sample size is 5 for this. 5 is not very good. If our sample size is at least 30 on a mean problem, then the central limit theorem says, oh yeah, the sampling distribution is approximately normal. So 5 is not even close. We do talk about graphing your sample data and looking to make sure basically that it's not super skewed, doesn't have any outliers. But when you only have 5 data points, it's not really great either. So we could do that and be like maybe like moving forward with it, but it's not great when your sample size is that small. But if the population is normal, if we know the population is normal, it doesn't matter what our sample size is, it's always going to be approximately normal for our sampling distribution. So if we happened to know that the observations are from a normally distributed population, that'd be great, because then my low sample size wouldn't matter anymore. I'd already know the distribution of the sample, the sampling distribution, I should say, will be approximately normal. Condition 2 just says comes from a random sample. All of the inference we do, confidence intervals, etc., in this second semester of AP Stats is under the assumption of an SRS, simple random sample. If you do like a stratified sample or something like that, there's fancier things you have to do with this that we don't cover in AP Stats. So we do need it to be an SRS. The third one says standard deviation is known. That would mean we know real sigma. If we knew real sigma, we'd be doing a normal problem for means. We talked about how when we know sigma, we would actually do a sample mean problem. But we don't need to know sigma because we can just use S, and S lets us do the t distribution instead. So we don't need to know the standard deviation of the population. We can just get by with S and use our t distribution, making the correct answer for this one, D. You need conditions 1 and 2 on this list. All right, so on to our second page here. We talked a little bit in the first page of this study guide about the connection between a confidence interval and a significance test, and that's what this problem right here is getting at. They made us a 95% confidence interval for the hypotheses p equals 0.25 versus p not equals 0.25. You can only go back and forth between confidence intervals and significance tests in this class if it's a two-sided not equal to test. If my alternative had a less than or a greater than sign, you would not be able to readily translate into a confidence interval form. So anyway, the interval goes from 0.26 to 0.35. We're 95% confident the answer is between those two numbers. Well, my HO was that P is equal to 0.25. That's not inside the interval. So because my interval does not capture the value from HO, we have convincing evidence that the HA is actually true. And now that I'm looking at this, they have a typo on that. That should say HA right there. We have convincing evidence for HA. So if we have convincing evidence for HA, we're going to reject HO. That's what we would do in this problem. So we would want to reject HO. If you reject HO, it means that your p-value is lower than your significance level. The p-value is smaller than alpha. So in this problem, they said that they made a 95% confidence interval. That is equivalent to the 0.05 significance level. So alpha is going to be 0.05 for this problem. Think about if you have a curve with 95% in the middle, there's 2.5% in each tail. So a 95% confidence interval is the same thing as saying alpha is 0.05. So if we reject HO at the 0.05 level, that means our p-value has to be something. They don't tell you what it is, and we can't actually find it. But we know for a fact our p-value is going to be under 0.05 because we already rejected at the 0.05 significance level. Here's the thing. We don't know if that p-value could be like 0.04 or it could be like 0.00001, like that. Either of those is a possibility for the p-value because all we know is that it's under 0.05. So if our p-value ends up being this guy right here, well, then we would not reject at the alpha equals 0.01 level. If it was like this guy over here, then yeah, we could reject at the 0.01 level. We just don't know. All we know is that it's under 0.05, which means the only conclusion I can confidently make in this problem is going to be I can reject at the 0.05 significance level. If they had an option like on this one, it says 0.10, you could reject at that level too, because it's 0.05 is lower than 0.10, but there's no other option that says that. So correct answer on this one is B. All right, getting into our good old friend type 1, type 2 errors and power and all that stuff, on to this next question here. So what they're asking us is we are looking at vitamin C in beans with freezing them and stuff like that, and we're testing the hypothesis that mu is 12 versus mu being greater than 12. You calculate the power of the test against the alternative. I'll explain that in a minute. And they tell you what the power actually is. So you need to remember with power, power is complicated, but you need to remember that power is avoiding a type 2 error. So when they talk about power, they're talking about avoiding a type 2 error. What does it mean to avoid a type 2 error? Type 2 error is when you fail to reject HO, but you're actually supposed to reject. So when I have a type 2 error, I should be rejecting, but I fail to reject. Power is not making a type 2 error. Okay, so we're avoiding a type 2 error. So what that means, and I probably want to write this down, even though it'll take me a second here, it's worth it. Power is rejecting HO. So it's rejecting when you should reject. It's going to take me a second to do this, but I want you guys to actually write this down because it's helpful. So power reject, I'm going to go add HO to that, when you should reject. All right, so we reject HO when we should reject it. That's what power means. It's avoiding a type 2 error. Now this 13.5 that they have in the problem, that's kind of weird. Like, where does that fit into things? Remember back in class, I talked about there was like a potato truck problem. And we talked about how if we think the answer is supposed to be 8% for the potato truck, and it's actually 9%, kind of hard to tell what's going on. That's called an effect size. It's not a very big difference right there. But if like 90% of the potatoes in the truck were bad, we would have an easier time rejecting the truck when we're supposed to. So they're telling us that the potato truck has 13.5. We thought it was 12. It's 13.5. That's basically what that number means right there. So this is kind of a long-winded way for me to explain that when you look at power for this problem, it is going to be the probability of concluding that HA is true. So we're going with HA. When you look at power, you're rejecting HO. So you're convinced by HA when you should be convinced by it. So I am going to conclude that the true mean is higher than 12. I'm going to go with HA when actually it is higher. They said it was going to be 13.5 in the problem. There was a little script for this in your notes somewhere at the end of chapter 9. You may want to look that back up, but you're rejecting HO when you should. That's the concept of power. So our last multiple choice question right here wants to know, it's basically tying in the concepts of error and probability of making those errors. And let's read through these statements and I'll talk about them. First choice right here says the power of a significance test depends on the effect size. We learned when we talked about power, there are 3 ways that you can influence and increase the power of your test because you want it to have high power. You can increase sample size. You can increase your significance level. So you can go from like 0.05 to 0.10, because what that does is it takes less strong evidence for you to reject HO. So you're going to reject HO when you're supposed to if you raise your significance level, but that makes you more likely to make a type 1 error. And the last thing was that weird word effect size, which I've used a couple times in class. Effect size is the difference between what HO says it is and what the truth actually is. And I just talked about this in my last problem. If you look at that potato truck example again, if it's 8 versus 9%, I might not catch that it's a bad truck. But if it's 8 versus 90%, I'm going to catch it. So effect size definitely does help your power. That's a true statement. Second one says the probability of a type 2 error is equal to the significance level. The significance level is alpha. That is actually the probability of a type 1 error. Probability of type 1 is your significance level. So you can directly control what that's going to be. So they used the wrong type error right there. That's not a true statement. That was type 1. And the last one says error probabilities can be expressed only when a significance level has been specified. That is also a true statement. Type 1 error just straight up is alpha. So you have to know that. And then one of the ways that you can increase the power of your test is by raising your significance level. So you need to know alpha before you can talk about the probability of type 1 or type 2. So choices 1 and 3 are both correct. That makes the answer B for this one. Again, a few of those multiple choice questions were a little trickier. I didn't put too many like soft toss multiple choice questions on this chapter here. So no worries if some of those were a little shaky. Now, going along with that trend, the problem I have right here for you guys that we're going to talk about is actually an investigative task, a number 6 question from a recent AP test. This is from 2018, so not very long at all ago. And it's a really good question, but it's also a little bit tricky, which is why I wanted to make it one that I talked about with you. Okay. So make sure you've tried at least part A yourself. That one's not bad. That's just mentioning type 2 error. And most problems that are number 6s start out with something easy before they get into the new, different, teach you something stuff. So this problem is looking at blood pressure at this big company. And across the country, the average adult blood pressure is 122, whatever units it's in. But this company is wanting to know if their employees' blood pressure is actually higher on average. So they'd want to take some steps to fix that if that was the case. A type 2 error. Remember what we talked about. Type 2 error means you failed to reject. So if you failed to reject, but you made a mistake, that must mean you were supposed to reject and you didn't. So what that would mean in context right here, when we're talking about a type 2 error, we failed to reject. So in other words, we did not find convincing evidence that the true mean is greater than 122, which is the national average, when in fact it is greater than 122. We failed to reject, but we should have rejected, and there's the context for it. You can look back in your notes and we have a script for that if you haven't done this in a little bit, but that's not so bad to do. They didn't ask for a consequence here. A lot of times they will. In this case, if I was going to talk about a consequence, the employees are actually in a risky health situation, but the company doesn't find that they are. So they're not helping the employees get better or lower their blood pressure when it would be a useful thing for them to do so. All right, so part A, not so bad, just starting us off, building our confidence a little bit. And then things get a little tougher with the rest of this question here. So this next question is talking a bit about a sampling distribution. So they want to know, they give us the standard deviation for the population, they give us the mean, they give you sample size, and then they even do, they're kind of nice right here, they give us the fact that for our sampling distribution, we would have to take sigma over root n. They already did that for us. So if you take your 15 divided by square root of 100, they told you the stats for the sampling distribution, and this is going to be for a sample mean. So we're going to look at this problem right here. We are assuming that the mean of the company is no different than the mean of the population. That's HO way up here, which says that the mean is 122. So we assume that this company has a mean of 122. And then once we have that in place, we're looking at samples of size 100 and a standard deviation of 1.5. They want to know what values for the sample mean would represent sufficient evidence to reject the null hypothesis at the significance level of 0.05. So wrapping your head around what it's asking you takes a minute when you read through it. Our HA was that mu is greater than 122. They want to know what value goes on my distribution. So I'll put like a little line right there. I don't know what this value is right here, but they want it to be where our results are significant at the 0.05 significance level. Since it's a one-sided test, this area right here would have to equal 0.05. So let me restate what this is saying right here. The question is asking us, in samples of size 100, if we take a sample mean from a group with a mean of 122, where the mean is actually 122, what value would it take for us to reject HO? So in order to do that, we would have to do an inverse normal on this problem. We would do inverse normal because we know that area is supposed to be a 0.05 on the right side. So when you set this up, make sure with your inverse normal, if you're doing a left area, it's going to be a 0.95 for that setup. And then you can write out the mean and the standard deviation from the problem, the 122, the 1.5. If you do that on this problem, what you end up getting is 124.47. So we have 124.47. Now, I went to an AP conference right after this test got released that next summer, and there was actually a little bit of drama with the scoring on this question right here. So the answer to the problem is 124, and if you did what I wrote right here, I would give you full credits. But the rubric for this test, I usually agree with the rubrics, but they made you find a z-score if you wanted full credits. You don't need a z-score to do this problem, so I wouldn't worry too much about that. But my general advice to you would be, if you're ever in a situation where you're doing normal CDF stuff, throw down a z-score anyway. It's not going to hurt you. But I didn't agree with the fact that they made you show this value. So if you were going to show the value on this, you would have to take your 124 number, and then you would subtract out the mean and divide by your standard deviation. So if you do this right here, which again wasn't necessary to get the right answer on this problem, you get a z-score of about 1.65. So yeah, the value you need before you reject is right there. Let's go on to part C right here. Using the actual mean of 125, the results from part B and the results from part B determine the probability that the null hypothesis will be rejected. And this is assuming, like they're talking about right here, in the company, the blood pressure is actually 125, an average of 125. Okay? So at this company, the average blood pressure is actually 125. So in reality, the company has an unhealthy blood pressure on average. And they want to know, looking at this problem right here, what's the probability that we reject HO? In the last problem, we just found out the value that would lead us to reject HO. They're making us use part B, which we just got, was this guy right here, that 124.47. So we want to know from 124.47, my video is probably running a little long right now, and I apologize about that, but we're going over some really useful stuff for you guys here, so hopefully you're still with me. So looking at this problem, at the company, the mean is 125. We will reject HO. We just found in the last problem, you'll reject HO with anything over a 124, because the company doesn't know the answer is actually 125. They go in assuming 122, and we just found that value in the last part. So if the value is 125 in reality, everything from a 124.4 up is going to make them reject HO. And as you can see, that's going to be a decent chunk of the picture right here, certainly more than half of the time. So if the company really isn't doing so well with their blood pressure, and it's actually 125, there's a pretty good chance that the company is going to catch it, okay? Because they're going in with the assumption, oh, are we 122? And 122 to 125, that effect size again, is a little bit bigger here. So if you do a normal CDF on this one, you would still do your standard deviation of 1.5 and all that. I'm not going to make you guys watch me write that out. Your normal CDF with a lower of 124.47, et cetera, gets you 0.64. Okay? So that is going to be the probability that they'll correctly reject the null hypothesis. Part D is a one-word answer right here, and it's a word I've used several times in this video already. So this is kind of the theme of Chapter 9 review here. What statistical term is what we just found? The company's blood pressure on average was bad. It was 125, higher than it's supposed to be, higher than national average. We want to find the probability of correctly rejecting HO, which is that it was 122, when we should reject because it's higher than 122. It's 125 in reality. That is absolutely what the concept of power is talking about. Calculating power Finding it but from like scratch is not something they make you do in AP Stats. It's too complicated. But this problem kind of walks you through how you can calculate power in a unique situation here. Not something you probably could have handled 100% on your own, but it's an interesting question. Quick fact on this problem here, and I know I'm going long, I'm almost done. The average score on this question in 2018 was less than a 1 out of 4 across the entire country. So the entire country, I think the average was like 0.8 out of 4. So this is a tricky problem right here. But hopefully you're learning a little something from it as I go over it. All right, let's finish this off. They're starting out with a sample size of 100. That's what this whole problem has been. Now what they're doing is they're finding if the probability of rejecting HO, so our power, would go up or down if they increased the sample size to be greater than 100. So the idea is if we increase our sample size, what is going to happen to that probability, our power? And of course, you guys should know just from memorization that increasing sample size increases power. That's one of the 3 ways to do it. But they're looking for a little more depth than just that. So what I said for this problem right here, if we increase our sample size, so the company is actually a 125. That's their reality, okay? If the company is actually a 125, our standard deviation used to be a 1.5. But if you increase your sample size, the standard deviation is going to go down because you're dividing by square root of n, and n is a bigger number now. So if your standard deviation goes down, we had that 124 number, 124.47. Fewer values are going to reach that ugly cutoff of 124.47 if the standard deviation is smaller. Because our mean is at 125. If we have a smaller standard deviation, we're not going to hit that 124.47 as frequently. All right, so my answer for that question is right there. Again, a little bit of a challenging chapter, harder than the average problem from chapter 9, but hopefully it's helped you guys with some of that tougher stuff you haven't thought about in a while. Thanks for listening.